check. My check. 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 My check. 1 2 3 4 5 6. My check. Check. My check. 1 2 3 4 5 6 3 2 1. Mic testing. Check. My check. 1 2 3 4 5 6. My 3 2 1. Check. Check. My check. 1 2 3 4.
there are two things which I wanted to tell in this class. Once that is switched on, I wanted to see how far I can go in the board, because some of the things which I write there are not coming, right? Is that so? Okay, it's fine. Then you are able to see at least. Okay. So there are two things which I wanted to complete the issues about the angular momentum, and I want to go into at least an introduction to perturbation theory, time independent perturbation theory, and that will essentially be less than what I wanted to tell in this course, and hopefully I wanted to go into time dependent perturbation theory also for the course, but I don't think I can do that as of now. So these are the two things which I wanted to explain. So the first part is about angular momentum L and L square and Lz, and L states are L square L comma m is L into L plus 1 into L comma m, and Lz Lm is m times L comma m. These are the states. This probably you are able to see something board? No, I have not said anything much. So spin half is that L is supposed to be, I will call it L, is actually people call it S in that case, half sigma, half h bar sigma if you want, is the generators of spin half rotations which I gave you. Excuse me. Oh, this is not seeing. Hello. Spin half is, let me try to tell as much as possible, half sigma. So there is a two states, 2j plus 1, 2s plus 1. Spin half is 2 into half plus 1, two states. One we will call it as one spin up, another we can call it as spin down. In vector space notation we will say 1 0 and 0 1, the vector with two this thing, and it is always acted on by a 2 by 2 matrix which rotates the spinors, which corresponds to rotation of whatever you do in 3 dimensions is reflected in the 2 component in a complicated way. Okay, something has come. Is it visible? Okay. So this is what you have here, and I can go to spin 1, spin 2, spin 3 by 2, spin 5 by 2, all of them. And in relation to that, I also gave L plus minus acting on L comma m will give me a new state which is m plus 1, m plus or minus 1 because I have put plus or minus 1 here, and this is a square root here L into L plus 1 minus m into m plus or minus 1. That is the relation. So in which case you can write the matrix. Matrix is easy to write from here. In the case of spin half, the matrices are 1 minus half for Lz because the spin up and spin down, and you also have 0 1 1 0, that is one of them, and then 0 I minus I 0. So the 3 matrices, and that is what you have written. You can write that for 3 by 3 matrix, 4 by 4 matrix, 5 by 5 matrix, all of them are representing angular momentum. Okay, all of them are representing angular momentum, and half integral ones are called spinorial representations, spinar representations, and integral ones are the integer angular momentum. And the particles which you have spin half nature are called fermions. It has an intrinsic spin half nature, and there are particles with integral spin, and they are called bosons. Do you know any particle which has integer spin? Photon has spin 1. Okay, photon has spin 1, and there are other particles now which are in elementary particle stage. There are spin 1 particles are there, plenty, gluons are there, W bosons are there, all those things are there in particle physics. And spin half, there is electrons, protons, neutrons, quarks, all of them are spin half, intrinsic in the sense that that particle has mass and spin, and all particles have both mass and spin. Now one small question which I will ask, which I will not answer, he also mentioned just now, the photon, okay, photon has spin 1, okay, we know it now, has spin 1. Now how many degrees of freedom should it have? A photon should have how many degrees of freedom if it is spin 1? Yes? Why are you not answering? I gave you. I am deaf. Tell me, how many degrees of freedom photon should have? 3. It should have 3 degrees of freedom, as you say. But really, does it have 3 degrees of freedom? How many it has? Photon. Photon is part of electromagnetic wave, right? Maxwell's equation, Indumati might have mentioned to you, or if she has not mentioned, she will mention it today, and it is given by so color, okay, thank you very much. I will use the blue also. Is it better? And let us see which is better, and let me see, yes. Among the 3, which is nice for you? All are okay? So that is the thing. So spin 1 is expected to have 3 degrees of freedom, and electromagnetic field as such as electric field and magnetic field, which is what photon is. Photon is supposed to be quanta of electromagnetic field, and the electromagnetic field, when it goes along some direction, the electric field and magnetic field are in the perpendicular directions. They are supposed to be waves in the perpendicular direction. They oscillate like this or they oscillate like this. That is what it does. Okay? So the electromagnetic waves oscillate in 2 directions in the perpendicular to the direction of the wave motion. So it means it has 2 degrees of freedom. It has 2 degrees of freedom, but you just now told me it has spin 1, it should have 3 degrees of freedom. So what is the controversy? I am not going to answer that. And it happens, I am not going to answer except making one remark. And that remark is the photon has 0 rest mass. The mass of photon is 0, whereas mass of all other particles are non-zero. So that makes the distinction. A massive particle, spin 1 particle, will have 3 degrees of freedom. A massless spin 1 particle like photon will have only 2 degrees of freedom. And they are called helicity in some sense. It is called helicity, that the perpendicular to that, that is the thing, that is the component in the direction of this thing is only plus or minus 1, that is what is there. Okay, this is basically the idea. Okay, so that is as far as this thing is concerned, and it is a slight detour. Now I am going to take the next level, that if I give two particles, a composite system, one with J1 and another with J2, angular momentum. Okay, it can be two electrons, it can be an electron and a proton, okay, a composite system. What are the possible angular momentum for the composite is the question. Now such things happen in, for example, nuclear physics. In nuclear physics, inside the nucleus there are several neutrons and several protons, okay, several neutrons and several protons, and the total spin of the nucleus can be a combination which is coming from all of them, because you are not looking into the details of internal details. Okay, that is what happens. So what are the possible ways? Now first of all, let us take two spin half, both J1 is half and this is half. I will put a circle in front of it to say that combination is half. What kind of combination we will see. Okay. Now how many states this will have? So the first spin half will have 2 states, the second spin half will have 2 more, so there will be 4 states. Unfortunately, the problem with 2 is 2 plus 2 is 4, 2 into 2 is also 4. So would you say it is 2 into 2 4 or 2 plus 2 4? Well, let us say, twist the question. I have a spin 1 particle with 3 degrees of freedom and a spin half particle with 2 degrees of freedom. So what is this composite system going to be? 6. So 2 plus 3 is only 5, 2 into 3 is 6. So what is it you should say for 2 dot 2? Is it 2 into 2? Okay, that is what is the 4 degrees of freedom. Okay. So what are the 4 states possible for you? First can be up and the second can also be up. Okay, second can also be up. The first can be up, the second can be down. Then the first can be down and first can be up. Okay, this is the thing. I have written those two side by side, you will understand immediately why. The last can be, both can be down. Okay, both can be down. Both can be down. Okay. Now if you want to think in terms of yesterday's direct product which I mentioned to you, 4 states, you should think in terms of this one is 1 0 and this one is also 1 0, and it is a direct product of these 2 states. If you want to think in terms of that, this is the way the state is to be labeled. Both are. Why is it I have given here side by side is, what is the magnetic quantum number of the total thing here? What is the magnetic quantum number of this and this together? 0. What is the magnetic quantum number of this also? So there are 2 states with magnetic quantum number equal to 0. There is only one state with magnetic quantum number is equal to +1, and there is only one state the magnetic quantum number is -1. So the fact that magnetic quantum number of the total becomes maximum becomes 1, minimum becomes minus 1 tells me that there is a spin 1 particle. But the spin 1 particle should have magnetic quantum number 0 also, right? 2 spin ups. So these two things are fine. This is, I will call it as total J is equal to 1 and Jz, let me call it, is equal to 1. That corresponds to that. And this one corresponds to J is equal to 1, Jz is equal to minus 1. These two, there is no ambiguity at all. There is only one state with plus 1 and minus 1. But there are two states here. One of them must correspond to J is equal to 1, Jz is equal to 0. Okay? That will be there. Now the question is which one? Which one? If I want you to find how to find that, I will give you. But there is some intuitive reasoning you can have to find out which one. Unfortunately, it is not one or the two among the two, it is a combination of the two. So what is that combination? Yes? Can anyone guess? Just intuitive guess. Huh? What is it? Sum of the two, yes. I can sum with one with some 1 by root 3, another with 2 by root 3, or 2 by 3 or something like that. Which one you prefer? 1 by root 2, yes. Okay. So the combination which is corresponding to that is plus here, 1 by root 2. Okay? So that is the combination which gives that. He is right. But there are 4 states. So you can't just throw away something. So you should take a state which is orthogonal to this combination which you have chosen and call it by a different name, right? And that is, I will write down finally here 1 by root 2. And you can easily see this is orthogonal. This is orthogonal to this. Is it easy to see? Right? That vector is orthogonal. That is, you take the dot product of this and this, you will find it to be 0. Okay, as a vector. For example, you put the ket of this thing and the dual vector on that side, you will find it to be 0. It's not very difficult to see. So this corresponds to, I'll give you, it corresponds to J is equal to 0, Jz is equal to 0. That's the difference between these two. That's the difference between these two, right? So you have 4 states which are given by 1, 2, 3, 4. These 4 states form a basis. They are nice bases. And this is also a basis. These 4 also is the basis. But this basis is nice in some way. This tells me it is spin 1, these 3, and this tells me it is spin 0. Okay, it tells me it is spin 0. So we would like to find out what is the link between these two bases. Like what is the link between these two bases? And the link is given by this coefficient here. 1, 2, 3, 4, 4 states. A linear combination here and a linear combination here makes this is one state and this is another state. And this coefficient comes with the factor 1 by root 2. There is a general name for that number 1 by root 2 from one basis to another basis, right? That name is, they are called Clebsch-Gordon coefficients. Clebsch-Gordon coefficients. They are nothing but Clebsch-Gordon coefficients. Okay, so this is what is the thing. So I can pose this question in very general terms. I can pose this question in very, very general terms, what I did for spin half. What I did for spin half. I start with, so J1 and M1 is one particle with spin J1, angular momentum M1, and that M1 will go from minus J1 to plus J1. Maximum will be plus J1, minus J1 will be the lowest. Is that clear? Now I have another state here, which I will put with a bracket thing here, J2 M2. J2 M2. There are two angular momenta, one is J1, another is J2, and the combination of both of them together is what I am looking at. Okay, composite of both of them together. Now tell me what is the size, how many states will be there? How many states will be there? 2J1 plus 1 into 2J2 plus 1, the product, like the way we did for 2 into 2 and 2 into 3, all those examples. That is the size. Okay. Now the question is, like in this case, when I combined two spin half, I had a spin 1 and a spin 0, right? I had a spin 1 and spin 0. Like that, I can ask the question, what are the spins that will be available? What are the spins that will be available? Okay. Now we can intuitively start arguing. We started with this particular thing, which is a unique state, right? There is only one state. Like that, I can start with J1, which means plus J1, and then another one with J2 and J2. Both are maximum. Magnetic quantum number is plus J1 in the first one, magnetic quantum number in the is plus 2 for the J2 for the second one, and maximum. Both are only unique. There is no other way to get what will be the total magnetic quantum number? J1 plus J2, magnetic quantum number, J1 plus J2. There is no way to get that by any other combination. So this state is unique. It is exactly as unique as this. The last one, I will write it here, J1 minus J1, and then cross J2 minus J2. Minus J2. So what is the total magnetic quantum number of this object? It is minus of J1 plus J2, right? So you start with minus of J1 plus J2 to go up to plus J1 plus J2, right? So there should be a particle or composite angular momentum with angular momentum is equal to J1 plus J2, because that will go from minus J1 plus J2 to plus J1. So there should be one total angular momentum where J is equal to J1 plus J2. That should be there. Total thing is J1 plus J2. It has to be there. Now what are the other things that can be there? That is the question. Okay. Now yes, it has to be, since it is maximum, you cannot go beyond that. So it has to be less than that. It has to be less than that. So what is the lowest that can be there? The lowest that can be there is J1 and then the other one is minus J2, or minus J1 and plus J2. This is the lowest that can be there. Maximum of first one and the minimum of the second, or this, which is actually J1 minus J2. So the angular momentum lowest that can be there is J1 minus J2. I don't know which one is positive and which one is negative. So I will write as J1 minus J2. So let me write it here. J is equal to J1 minus J2 mod. I will write it as mod. For practical purposes, I can say J1 is greater than J2, so it is J1 minus J2. So you will have J1 plus J2 and then J1 minus J2 as the lowest. So the angular momentum of the composite will go from J1 minus J2 to J1 plus J2 in steps of 1 unit each. 1 steps of 1 unit is. So the total thing is going to be J is equal to J1 minus J2 mod, comma J1 minus J2 mod plus 1 dot dot dot, finally J1 plus J2. Okay? Finally J1 plus J2. That many states will be there. Angular momentum, a better basis than the previous basis. We said that our basis consists of 2J1 plus 1 into 2J2 plus 1. That is the total number of states. The total number of states are not changed. Here, even here, the total number of states is only 4. And the total number of states is only 4. Both should be equal. Okay, both should be equal, otherwise it is wrong. So you wrote this as 2 into 2, which is 4 states, 1, 2, 3, 4 states. You wrote it as 2 into 2 is written as 3 plus 1. This is 3 and this is 1. Like that, you are going to write it. This one will have 2 into J1 minus J2 plus 1. This one will have 2 into J1 minus J2 plus 1, this whole thing plus 1. Okay? And then go on. And then finally 2 into J1 plus J2 plus 1. Each one of them will have this kind of dimensions. You just have to take the spin, multiply by 2 and add 1. Take the spin, multiply by 2 and add 1. Take the final spin, multiply by 2 and add 1. This is the dimension of each of the angular momenta. So one identity which you should verify, simply a mathematical identity is, if you add all of them, okay, if you add all of them, what is it you should get? You should get 2J1 plus 1 into 2J2 plus 1. That is an identity. It is like saying 2 into 2, 4 is written as 3 plus 1. Okay? That kind of identity is what you should do. That is, try to add all of them, prove that it is equal to 2J1 plus 1 into 2J2 plus 1. That is the first part. Is that clear? So I am trying to finish it fast so that I can go to time independent perturbation theory. So this is the first part. And you can ask the question, what is the relationship between the bases? Now this one is unique. This one is unique, which corresponds to J is equal to, this corresponds to J max and J max state. This state corresponds to maximum value of J, and the magnetic quantum number is also maximum. That is unique, correct? I want to get the next one. Which I have got from here. From this I should get this, and from this I should get this, correct? How do I get it? To see that, you can see some interesting thing here. This is up and this is also up. If I interchange this, does anything happen? Both are up. Now what about this? This is up and this is down. This is down and this is up. I interchange both. Does anything happen? No. So whatever symmetry, permutation symmetry of this is there for this also. It is there for this also. All the three have the same permutation symmetry. Okay? Permutation symmetry. There are another way of getting this. There is another way of getting this from here. Okay? How do I get this? Get from this is the following. To get from this to this, what I do is I take this state, I can act on this state by L minus of the first spin or L minus of the second spin. So I can do the L minus of the total of J minus is J minus 1 plus J minus 2. I take this, right? J minus of 1 plus J minus of 2. So I act on that. So when I act on this by this, I will get this state. This one will give me this state and this one will give me this state. Because when I say J minus act 2, acting on that changes the second one to up to down, one step down. Is that clear? Similarly, J minus 1 will change the first spin to down. It doesn't touch the second one. It doesn't touch the second one. So that is the way I get the next one and so on. Okay, that's the way. So that is the way I can do here also. To get from here, I can get J1 minus 1 plus into J2 plus J1 J2 minus 1. What is the magnetic quantum number of this state? J1 plus J2 minus 1, correct? You have to add this and this together. J1 plus J2 minus 1. What is this one? That is also J1 plus J2 minus 1. So in order to go from here to this, you have to act by J minus 1 plus J minus 2. That's what you have to do. Okay? In the previous example, that action gives rise to that 1 by root 2 factor. 1 by root 2 factor. It will not give for a generic case. We know the formula, which I have probably written down, and that formula which I have erased here, I will write it here. L minus J minus J m will give me square root of J into J plus 1 minus m into m minus 1, because that's minus sign here, and then J m minus 1. That is the formula. Okay? The factor is J into J plus 1 minus m into m minus 1. Okay? That is the formula. That was giving 1 by root 2 previously. Now it is giving rise to a different number. Like that, you can find out the next state, which is here, which is this one. And again act on this by the same thing, you will get this. If you act on that again, it will get 0. It won't go below that. That's what is there. So the next higher state is, as I told you, if you have the maximum, so maximum, you can go below that, J1 plus J2 minus 1. That one, both of them have the same angular momentum, but it should be orthogonal to this state already. It should be orthogonal to this state here. Find the orthogonal combination of those two states. Then that will be automatically J1 plus J2 minus 1. Like that, you systematically construct all of them. So the general formula linking, that's what is called the Clebsch-Gordon coefficients, and that's what is I am going to write down. So the general formula is J1 M1 colon J2 M2 total producing, so this is, let me put J1 M1 comma J2 M2 colon producing J and M, correct? J1 M1 and J2 M2 produces for me a number between J1 minus J2 to J1 plus J2, and that's what I call as J. The corresponding magnetic quantum number will be a number between two J1 minus J2 plus J. This is the state, and that state is equal to sigma, just like sigma is like this summation of the states which I have, which is going to be a linear combination of J1 M1 into J2 M2, and there are coefficients here which I will write it as CJM and then J1 M1 J2 M2. This is the coefficients. Combining J1 M1 and J2 M2, I produce Jm. That's what this coefficient is telling. That coefficient is called Clebsch-Gordon coefficients. Obviously, M should be this M which you have here, this M which is here should be equal to M1 plus M2. If M is not equal to M1 plus 2, it will be 0. That coefficient is 0. So like that, you will have these relations. You can work out for arbitrary combinations. You can, as a trial, you can work out for a spin half and spin 1. I have already done for 2 spin halves. I always take the simplest example. The next example is, one of them is spin 1 and another is spin half. One level higher complication. So try to do, because there are 6 states. Spin half and spin 1 will give you what are the possible angular momenta. You will have what is the total angular momentum can be, 1 and half. So it should be 3 by 2 maximum. You should reduce by 1 unit, only half. So it can be a half and a 3 by 2, spin half and spin 3 by 2. Spin half will have 2 states, spin 3 by 2 will have 4 states, 4 plus 2 is 6, which is same as 2 into 3. 2 into 3 is equal to 4 plus 2. So it's more or less similar to that, it's one level more complicated, but you can write down the most general formula which I have already written down and write down the states. Okay? So try that as an homework or something, try to do it for your own benefit between spin half and spin 1. Okay? That is the point. The last point which I wanted to tell is, this is for a composite system of 2 spin halves, for example this case, okay, 2 spin halves. Now I can start with the composite system with the spin 1, and it has, let us say, spin 1, I start with this state. I start with the spin 1, Jz is equal to 0 state. That particle splits into two particles. One of them is spin half, another is also spin half. But the total angular momentum is fine. Magnetic quantum number is Jz is 0. So the magnetic quantum number is also conserved. So when it splits into two, one here, if this is spin up, this has to be spin down. If this is spin down, this has to be spin up. Okay? Now, let us say I have the system here, spin 1, with magnetic quantum numbers Jz is equal to 0, split into 2, and then this thing is spin half with up spin or down spin with nothing. I take the other particle to far away place. Okay, far away place. I take this object which is spin half, I make measurements here to find what is its spin, because it is an ensemble of various spin 1 particles. All of them split into two spin half, some of them go in one direction and some here. I make measurement here. When I make measurement here, if I find it is spin up here, that object which is on the other side has to be spin down, right? Because this state which I have written down is what is called entangled state. This state is entangled with that one, even though it is locally separated. Okay? Even though this is state here with, so what I have done is I have started with H1 cross H2, two Hilbert spaces. I take the H2's part again further, and H1 is here. I make measurement here, I try to understand that. I can understand that way, provided this state which you are considering is entangled with that one. For that, this particular state which you have here and this particular state is product of the two states here. One here, then it becomes automatically different Hilbert spaces. Okay? There is no link between them. This can be up and that can be down, various combinations, because it's all ensemble. But when you do this kind of states, you can never write this state which is J is equal to 1, Jz is equal to 0 as a state in Hilbert space 1 cross a state in Hilbert space 2. You can never write that way. It has to be a combination. Okay, it has to be a combination. That is actually the definition of what is called the entanglement. That is we call it bipartite system. We are bipartite because there are two Hilbert spaces. And then the total Hilbert space has lot of states. Some of them can be written as a product of one state here, product of another state here, like the first one. Some of them cannot be written in that form. It has to be linear combination of some state here with thing and linear combination of that. That's what makes life complicated, and that bothered people like Einstein, Podolsky and Rosen, EPR, what is called. They wrote similar thought experiment, Gedanken experiment, that this thing by measuring here I know about that, and similarly other way. So this led to a lot of better understanding of quantum theory, because quantum theory has some inherent non-locality about it. It's always not local. There is some inherent non-locality about the states and information which is going in. I cannot go into this more than that for the introductory course in quantum mechanics. So I am going to stop here. If you want to have further discussions, if possible, we will try to have it. So is that okay? You have any other questions up to this? Because I am going to do time independent perturbation theory for the next 45 minutes. Any questions? Yes? No? Okay. Okay, so now I am going to do time independent perturbation theory. I hope I have it here. Okay. I will try to explain simple example and then go into formal way in which it is done. Okay. For a simple way is simple, as simple. What is it we want to do in stationary states? We want to find the eigenvalues of the Hamiltonian matrix. It's a self-adjoint operator or Hermitian operator. We want to find the eigenvalues of that operator. And some of the problems we can solve exactly. One such problem is the harmonic oscillator. So let me say it is harmonic oscillator. H is half p square plus x square. I have put h bar is equal to 1, k is equal to 1, all those things. If you want, you can put those things also, right? You can solve this exactly. You know all the eigenstates of that Hamiltonian. You know all the eigenvalues of that operator. There is no problem. But that kind of a thing is not always what reality is. Okay? What reality is not always this kind of problem. For example, if you have a molecule like carbon dioxide or something like that, for small vibrations you can get this way. For large vibrations there will be nonlinear terms. For example, I can have something like some lambda x power 4. I can add that term, some higher order terms for your confusion. That's what is there. We did particle in a box. Okay? Particle in a box is what? The potential is 0 and potential is infinity outside. That is what particle in a box. Now I said potential is 0 here. Let me write that example also. Particle in a box. H is p square by 2m, p square by 2 plus v, where v is 0 between x is between 0 to 1 is equal to infinity outside. This problem I solved it, or many people, all of you solved it, right? Now I say it is not 0. I say it is some, here it is some v is, instead of this I say it is lambda cos x. X is equal to 0 pi x, let me write pi x. Okay, that is a potential if I give you. At x is equal to 0, potential is 0, and at x is equal to pi, or x is equal to 1 cos pi is, I suppose it is 0, right? Huh? Okay, so let's make it a cos pi by 2. See, I miss all this trigonometric cos pi by 2x. Okay? So that is a form. Now can you solve it? That is the question, right? Answer is, unfortunately this can also be solved. You can solve it exactly also. The problem can be solved here and this, but the lambda x power 4 you cannot solve it exactly. For example, if I ask you to write down the Schrodinger equation for with lambda x power 4, you will have a Schrodinger equation, and then this thing is you can't solve it exactly. Analytically you cannot solve it. So what is it you can do? Or the other way is, I write a matrix H which is 1 A comma 0 0 B, or lambda 1 lambda 2. Let me write lambda 1 lambda 2. This matrix is diagonal. This matrix is diagonal already, right? There is nothing to solve. You have already solved it. What are the eigenfunctions of this Hamiltonian? Eigenfunctions 1 0 and then 0 1. These are the two eigenfunctions of that you have solved. Now I perturb it. I say this is some mu and mu here. Okay, I put mu and mu, or I can put mu and mu star if you want. Okay. So now I ask you to solve it. Find the eigenvalues and eigenfunctions of this matrix. Well, you can do it exactly because it's a 2 by 2 matrix. You can only solve it this thing. But I give you some 100 by 100 matrix, and I give you the eigenvalues of the some unperturbed matrix. All of them you write it down. Then I give some off diagonal terms. Okay, something along first one step away from it, and then ask you to solve it. Now, can you solve it exactly? May not be able to solve it exactly. Okay, some cases maybe, some cases. So it becomes problem. So you have to solve that kind of a thing by a method which is called perturbation method, perturbation series. What is meant by that is, I know the solution when lambda is equal to 0. I know the values are E0, E1, E2, E3, etc., E1, E2, E3, etc. Now, when lambda is very small, extremely small, by that extra term which is there, what do you expect? You expect the eigenvalues will be also very close to the previous eigenvalues. Okay? So, which means you can express, if this one has En as a eigenvalues, you can express that E for this problem as En plus lambda, some En, some first order, and lambda square En2. It's like expanding a series. You can expand it as a series up to infinite number of terms. You can compute it up to any order you like, so that then you are satisfied with the number of how many orders you want to solve. Maybe you want to find up to 10th decimal place, 5th decimal place, etc. For practical problems, that may be sufficient, right? If you want to find the spectrum and you want to find what is the difference between one level and another level, after all you are going to do experiment and find the frequency or wavelength, and how accurately you want the theory should give that difference. You may want it up to some 5th decimal place. 0th decimal place, it doesn't work out, because that's what experiment will show you. But you can find out 3rd decimal, 4th decimal, etc., etc., and you can call it as a perturbation series. You can call it as a perturbation series. Okay, that is basically the problem. You can do it in a series, order of lambda square, order of lambda cube, etc. Okay, even here you can do that, even though you can solve it exactly. Okay, so this is basically the program. So I am going to do the formal theory, and then okay, what is it I am going to do? My Hamiltonian is H naught plus lambda Hi. I write it as lambda Hi. Okay, where lambda is a small parameter, I know the eigenvalues and eigenfunctions of H naught. Okay, I know the eigenvalues and eigenfunctions of H naught. They are H naught Un is equal to En Un, and I will call it as 0 here to indicate it is the 0th order. There is lambda to the power 0. Sorry, lambda is 0, not lambda to the power 0. Lambda is 0. Okay, that's what is the thing which we know. Like harmonic oscillator, I know for p square plus x square, half p square, I know the eigenvalues are n plus half. There are many problems for which we know exactly. Even hydrogen atom, we know exactly. Various problems are there which we can do exactly. So these are the things which are there. Now what is it we want to find out? We want to find out H. I will call it as Vn is En Vn. This is what we want to find out. Okay? Vn to the lowest order will be Un. Vn to the lowest order will be definitely Un, because when I drop all powers of lambda, that's what you expect. So we expect that Vn and En can be expanded, can be Taylor expanded, let me put it as, in powers of lambda. That's what first assumption which we are going to have. Okay? Which means that infinite series which I am going to write down, that infinite series will be convergent. You know about convergent series? Right? Infinite series will be convergent. You can sum over. For example, you can find out, say 1 by 1 plus x, 1 plus lambda x, or 1 minus lambda x. You can write, for example, forget this, I write 1 plus lambda x plus lambda square x square plus this thing, etc., up to infinite number of terms. As long as lambda x is less than 1, if lambda x is less than 1, I can sum all of them and get the answer. Okay? But the radius of convergence is 1. That is, if lambda x is greater than 1, if I write each of those terms, when you add all of them, it will go to infinity. Right? If you add 1 plus lambda x, 1 plus the lambda x square, lambda x cube, etc., if I write all of them, then they will all adding up to infinity. It's a divergent series, because each term is growing up. Whereas if it is less than 1, it will not grow. Okay? The nth term and n plus 1th term will be much less. There are ways of testing whether it converges or not, a series will converge or not, by simple analysis, simple things, which is done in mathematical physics courses, which I will not do right now, but this is what is the idea about the expansions. Now you think that the radius of convergence is coming only because of that lambda x at equal to 1 becomes infinity. But lambda is equal to 1, it becomes infinity. The convergence problem comes only from there. Answer is not that way. For example, I can write down 1 by 1 plus lambda x, or 1 plus x square, 1 plus x square. Okay? Whatever value of x, real values, it doesn't blow up. It is always positive. There is no, it doesn't become infinity. Even for this problem, the radius of convergence is only x should be less than 1, even for that. Well, if you know a little bit of complex analysis, then this thing is because there is a singularity in the complex plane of x, the x real, x imaginary. In this plane, x square is equal to minus 1, so this is plus I and minus I. Plus I and minus I, it blows up. So it's only blowing up on the imaginary plane, imaginary axis. There is no singularity on the real axis. But even then, the radius of convergence is only 1. So you have to be careful about when we talk about something becoming infinity can come from some imaginary places. Okay, that's what is the idea. So be careful about that. Okay, these are all only side remarks, but what we want is we want to get this thing. Okay. So what I am going to write down now? So I am going to write down Vn is equal to so it is I am going to write it down as Vn0 plus lambda times Vn1 plus lambda square times Vn2, etc., etc. Okay, it expanded in series of powers of lambda. Similarly, I am going to write down En is equal to En0 plus lambda times En1 plus lambda square times En2 dot dot dot. Okay, I substitute now. So H is equal to H naught plus lambda Hi acting on Vn, I will write it as a series Vn0 plus lambda times Vn1 plus lambda square times Vn2, I will write only up to this and then put dot dot dot, is equal to En0 plus lambda En1 plus lambda square En2 plus dot dot dot, and again this whole thing Vn0 and then lambda Vn1 plus lambda square Vn2 and dot dot. Is this clear? Whatever I have substituted, I have only expanded my Vn exact eigenfunction, which I don't know. I expanded it in powers of lambda, and I don't know the exact eigenvalue En. I have expanded it in powers of lambda and substituted here. Okay. So what I am going to do is, let us look at the first thing. This is H naught, Vn0, En0 and Vn0. These four terms which I have circled, they do not depend on any power of lambda. So to the order lambda to the power 0, I can write down H naught Vn0 is equal to En0 Vn0. Vn0 to the order lambda equal to the power 0, right, or lambda equal to 0. Now we know already this solution, that Vn0 must be, you have already written down Un, right, because I know the eigenvalues and eigenfunctions of this thing. So Vn0 is equal to Un and En0 is equal to En, whatever I have here, to the first, to that order. Okay, is that clear? So next I am going to take to the first order, lambda to the power something. Now that h naught lambda Vn1, let me write h naught lambda Vn1, this with this, and then I have lambda I plus lambda hi Vn0, this into this is equal to En0 lambda Vn1, and then this is lambda En1 lambda En1 Vn0. So I can cancel this lambda. I can cancel this lambda, and I already know my Vn0. I know already my Vn0 is Un, right? I already know that. So that is also Un here. Okay, that's the point. Okay. Now what I am going to assume, which is easy to prove, is that this Vn, Vn1, Vn2, etc. are there. Let me put as I here, general one. Okay, it is orthogonal to Un. Let me put it as it's 0. Sorry, let me put it as 0 for all values of n and m. Okay, except for I is equal to 0. How do I do that? It is very simple exercise. You can easily argue. The state Vn can be expanded. Supposing it has a component in the direction of Un, okay, then put that. You find out for all up to all powers. You can bring that to this side and then divide it by that power of lambda and make it is independent of that one. That's all. That is as simple as that. Okay. So this, using this from here, from this thing, I will get the first result. And it is called a very interesting result. And the result is the following. En1, the correction to the first order in the perturbation is simply the expectation value of n in the for this extra thing which you have written down. The expectation value, if you want, I can write this as psi n star integral hi psi n dx. Well, it need not be dx, it can be dqx also, but that is the result. That is all, as simple as that. So in order to find the first order correction, you don't need anything more than what you already know. You know all the eigenfunctions and eigenvalues. If you know all the eigenfunctions un, find in that basis what is the expectation value of hi. If you find it, you will get the answer. You don't need to know what is the new eigenstate at all. We don't have to know what is Vn1. That is not needed. To that order, it's only this much. That's what is the thing here. When you want to find the second order, you need to know other things. but to the lowest order, the previous eigenfunction is enough. Okay, that is the first part about it. Okay. I am going to write it in the most general forms so that now from this, so this exercise whatever I have done, I can write down, I have written the zeroth order, I have written the first order, I can write down the second order. So there are every order of lambda I can write one equation. Every order of lambda I can write that equation. So I will write down for the lambda power 1 is going to be explicitly h naught minus En1, I suppose En0 acting on N1. This is what I have been writing Vn. Okay, let me write Vn1 is equal to lambda into E1 En, no lambda here, En1 minus Hi Vn0, that is Un, the first order, lambda square order. I will write one more for your benefit, which is H naught again minus En0 Vn2 is equal to En 1 minus Hi N1 V N1 plus lambda square, that is the En2, and Vn2. I have written only two orders. You can write it, the same thing gets repeated again and again. You can write to all orders you like, okay, all orders you like. Now the beauty of this whole exercise is, if you know up to order lambda to the power k, all the results, you can find to the next order. Okay, that is all that means. So the next order can be easily found by this thing, and that result from here is the following: En2 is equal to Vn0, which is Un, Vn0 is Un, and then Hi, I will write it as lambda Hi, and then Vn1. From the zeroth order first order calculation, if you find the first correction to En, which is what I have written down here, and the first correction to the eigenfunction from there, using those two, you can find out to the next order correction En square, and also the next correction to the state also. There are two things. One is the state is expanded and energy is expanded to order by order. When you do for order by order, if you know the results up to the previous order, using that you can find out the next order. And if you know this, you can go to the next order. So you can completely expand it to all orders you like. Okay, all orders you can like. This is a formal result. Formal result is what I have written down here. That is this one. I know Vn0 is my Un, this is my Un. Okay? The question is, what is Vn1? For that you should know the previous result. And I will write down the previous result. So I can write down Vn1 and then Um expanded in the basis of the previous basis, that is equal to Um Hi Un divided by Em minus En. Up to, yeah, zeroth order. So the correction, the first order correction Vn1 in the state is given by, find the, so you can write down Vn1 in some basis, some Cm Um, where Ums are H0 thing, and you want to find this coefficient Cm, and that coefficient Cm is given here. It's only the transition probability, what people call as the from N to M divided by energy difference. If the energy difference is too large, it's essentially when you perturb it, you won't go to very high levels. Okay, that's what this means. This is the result. So I will write down the formally the what is the thing, because of another 10 minutes is there, I have to conclude by some remarks. And En1 is this thing. I'll write down En2 for your benefit, also, which is interesting. En2 is minus Un Hi Um Hi Un divided by Em minus En. That's what it's. And this object is this object which is there in the numerator, it's mod of Un Hi Um whole square. It's only mod of that. That is the result. Now there is a negative sign which is interesting. The ground state, this is positive. The numerator is positive. The only question is Em minus En. If En is the ground state you are looking for, okay, that is always less than the higher excited states. So that is also positive. So this quantity which you have here for ground state is always negative. The second order correction is always negative for the ground state. Okay? So this is a simple result which will follow from what is called time independent perturbation theory. But there is one complication which I didn't tell, and that complication I am going to do in the next few minutes. That complication is, what happens if you have a state which is degenerate, right? You have degeneracy in the states, like in the two-dimensional oscillator, right? Then Em which you are trying to work out, which is the another state which is different from Un, you have a Um. Instead of that, and Un have the same energy, but even though they are different, because it is degenerate. Like in the two-dimensional oscillator, you had 1 0 and 0 1. 1 0 is different from 0 1 state, but both of them have the same energy. So when you divide by that E m, there is some peculiar thing which is happening. Okay, degeneracy, when there is a degeneracy, how do you handle it? I will explain that by a very, very simple example. Now, given all these things, I can try to do something in known exact, for example, I always said I can H naught, I know the solutions. H naught plus lambda Hi, H naught plus lambda Hi, I said that I don't know the solutions, so I have to do perturbation series, right? I have to do perturbation series. In some cases, we know even that exactly. For example, in the particle in a box, if I put a potential, and that potential is cos pi by 2x, even that problem can be solved. It is no longer perturbed. Well, it is perturbed, but that is not the thing. Okay? So this is the thing. So the interacting Hamiltonian with extra terms and unperturbed Hamiltonian both may be solved, and if there is a perturbation series, we should verify whether it works or not. And I will give you first simple example of that. Okay, the first simple example is, I want you to solve half p square plus x square. So can you solve this? Because you have done that so many times, harmonic oscillator, right? P square plus x square. So I am going to perturb that, I am going to add extra term to that. Now that extra term which I add is not the lambda x power 4, which is more complicated. I will write lambda x square. I write lambda x square. Okay? So can you solve this equation? Half 1 by 2 p square plus x square, for this the solution was En is equal to n plus half h bar omega. That is the solution. What is the solution? H bar is equal to 1, so I can drop that. Let me take h bar for me is 1, I will drop that. But there is a omega, which is k divided by m, square root of k divided by m, okay, which is also 1. So that's what you wrote. Now for this, I can write it as half p square plus 1 plus 2 lambda x square. Right? I take this lambda x square here. There is a x square into 1 plus lambda, but there is a factor of 1 by 2 here. So account that by 2 lambda. Right? That is the expression for the new Hamiltonian. So what is the new k value? New k value is 1 plus lambda, 1 plus 2 lambda. What is the new frequency omega? Square root of 1 plus 2 lambda divided by 1. So it is square root of 1 plus 2 lambda. So we know the solution for this also. We know the solution for this also, which is En is equal to n plus half into square root of 1 plus 2 lambda. Correct? It is as simple as that. That's the exact solution. Now what is it you can do? 1 plus 2 lambda to the power half, you can expand it in any way you like, perturbation series. So do you know the expansion for 1 plus 2 lambda power half? First term is the only one I know, that is the only thing, is 1. What is the next one? So is it plus or minus? Plus or minus? Minus. Correct? Plus or minus? Okay. Let me write 1 by 2 lambda. Correct? What is the next term? 1 by 2 into 1 by 2 minus 1 by 2 factorial 2 lambda whole square. So that is correct. So that is the result, up to at least second order which I have worked out. And you can see 1 by 2 into 1 by 2 minus 1 is negative. So the second order correction is negative for the ground state, which you expect. So this is the result which you have. And to all orders I can work it out. All the coefficients, I know En0, En1, En2, En3 up to infinity. Up to infinity you know the numbers, all the numbers. What is the function of n and lambda to the power n? I know the coefficients. And they all sum up nicely as 1 plus 2 lambda. Okay, 1 plus 2 lambda. And that's what you have here. Okay. Now the important thing is, if I do perturbation theory by the standard way, I will get each term, this first term is lambda, right? First term is n lambda, n plus half times lambda. That's what the first term is going to be. Second term is here, lambda square, etc. If I do perturbation theory, I will get all of them. And if that lambda x square, that if lambda is greater than or 2 lambda is greater than 1, I know the expansion is not valid. Binomial series of this type is not valid. And that infinite series which I get from there is also not valid. It's a divergent result. Even though it is a divergent result, I can find exact formula by summing up and putting that as 1 plus 2 lambda to the power half. 1 plus 2 lambda to the power half is a finite number even if 2 lambda is greater than 1. If 2 lambda is greater than 1, let us say 4, 1 plus 2 lambda is 1 plus 4 to the power half. It's only a finite simple number, root of 5, that's all. But if I try to expand it in this series, you will get an infinite series which is divergent. You will get an infinite series which is divergent, and your perturbation series also will give you only divergent series. From somehow, even if you work out a divergent series like that, like this expansion, okay, it's exactly like this. 1 by 1 minus x is 1 plus x square up to infinity. Okay. For x greater than 1, that right hand side is infinite series, divergent series. But if you have that series, you can rewrite that series in this form. Okay. This is what in complex analysis called analytic continuation. Analytic continuation. The series is divergent here in this region. You have another series which is there in this thing, and in the overlap region you can go from that to this one. I don't know whether some of you or all of you have done complex analysis, complex things. This is what is called analytic continuation, and that's simply an example here. Even though the series is infinite, this thing, I can reconvert it to this finite series and use that. There is no problem. Okay. And the last point is, before concluding, if I do for this example half p square plus x square plus lambda x power 4, if I do the same analysis, I cannot do it exactly. I cannot do it exactly. And you will have the first order, zeroth order, first order, second order, third order, etc. And you will get some result for something. Unfortunately, that series is divergent series, whatever be the value of lambda. It is a divergent series, whatever be the value of lambda. That's a pity. Which means you can't use the perturbation method at all. That's what it looks like. But unfortunately, for lambda small, each coefficient first initially decrease, and then the higher and higher, after some value, it increases. So first En0, En1, En2 decreases, for some value lambda is 0.1, decreases, and then it increases. So you can use this series up to this order till it starts increasing. Okay, this is what is called asymptotic series. You are not able to use the full series, but find out where it reaches its minimum. Find where it's thing, up to that you can use it. After that you cannot use the series because it will be divergent after that. Okay, this is basically the idea. And this is the problem of unharmonic oscillator, where in the complex analytic notation, that series which you have has an essential singularity at lambda is equal to 0. You can't talk about the radius of convergence in those cases. That is the next part about it. And the last part, which I can take only 2 minutes because there is no time, which I mentioned is what happens when there is a degeneracy. I will give you a simple example. I have a matrix 1, 0, 0, 1. This is my H naught. Okay? I know the eigenvalues. What are the eigenvalues? Both are equal to 1. Degenerate. What are the eigenfunctions? 1, 0 and 0, 1 is the thing. So this is what this thing. I now perturb it. And when I try to perturb it, I will put lambda here, lambda here. I have perturbed it. What are the eigenvalues? What are the eigenvalues of this matrix? What are the eigenvalues of this matrix? Can anyone tell me? Plus or minus? Is it true? First of all, the trace has to be 1, 2. The trace of, which means the sum of eigenvalues has to be 2 when you add all of them. You know this result? If you have a matrix, sum of eigenvalues is equal to trace of the matrix. Do you know the result or not? Yes or no? Sum of eigenvalues, which is going to be the trace of the diagonalized matrix, lambda 1, lambda 2, etc. The trace of the matrix and this will be identical. The trace of the matrix is 2, right? So that's what it is going to be. So 2. And the determinant of the matrix will be product of the eigenvalues. The eigenvalues are lambda 1 and lambda 2, determinant is lambda 1, lambda 2, and determinant of the matrix is same, it doesn't change. So determinant is 1 minus lambda square, right? 1 minus lambda square. So using this you can immediately say the two eigenvalues are 1 plus lambda and 1 minus lambda. It's only 1 plus lambda and 1 minus lambda. That's eigenvalues for this problem. You have solved it. There is nothing. But I want you to solve it by perturbation method. Right? To the order lambda, one eigenvalue goes down, another value goes up. Before that, two eigenvalues were equal. One of them go down and another goes up. This is what happens in spin electron in a magnetic field. Electron spin in a magnetic field, one of them eigenvalues go down, another goes up. Okay? And both are degenerate when the magnetic field is 0. When the magnetic field is 0, both are degenerate. But when the magnetic field is not 0, it has splits the degeneracy is lifted. Degeneracy is lifted. But perturbation theory, how do you do it? Because even though you can use unperturbed Hamiltonian as eigenfunctions, you said 1, 0 and 0, 1, right? But are they the only eigenfunctions? Any linear combination is also eigenfunction. You can have alpha times 1, 0 plus beta times 1, 0, 1 is also an eigenfunction because both are degenerate, right? So you have to find a suitable eigenfunctions, and then instead of using the 1, 0 and 0, 1, by which you can compute. So I will leave this at this simple exercise and try to find if I have in the two-dimensional oscillator which I gave you, right, p square plus x square, px square plus x square plus py square plus y square. We know it is degenerate. The ground state is not degenerate, there is no problem. The first excited state is degenerate and it has only 2 levels. And I perturb it by lambda x square. I don't put y square. Okay? I don't put y square. I can write down the Hamiltonian. I can write down the Hamiltonian and I can solve exactly, and it splits. The degeneracy of the ground first excited state will be split. That you can easily work out. So I will leave that as an exercise and I will stop here. Unfortunately, I could not go up to the next level, which is the time complete analysis of degenerate perturbation theory. Whatever I have done here, I can do for that also in the most general case. And secondly, I wanted to do time independent perturbation theory. It's like if you have a spin in a magnetic field, that mu dot B, okay, which you have. I suppose you know that, right? Magnetic field, if you have a magnet and if you have a magnetic field, the interaction energy is mu dot B, mh cos theta if you want, mu h cos theta. Now only thing is, if I say the magnetic field is rotating, you change the magnetic field, okay, then the problem becomes more interesting, which is called time dependent perturbation theory, and that leads to some interesting results. And when you then you can ask the question, is the time dependence very fast or sudden or slowly? Are you changing the perturbation slowly with time, small amounts, or immediately like a hit? I hit to the cricket ball, just hit it. Sudden approximation and adiabatic approximation. These two things will make a difference, and that's also interesting, but unfortunately I cannot do that. I'll stop here. Thank you very much. Thank you. You have any questions? I'll come down. So do you have any questions? I will be available till maybe around 9. And various other things. That's all that is there. Do you want to ask any question? Yes.
Lambda times xy.
Yeah, that's also there. For example, px square plus x square plus py square plus y square, some lambda xy. Okay, the two oscillators were disconnected. Okay, now this one will link both of them. That problem can be exactly solved because x square plus y square and then lambda xy all are quadratic. I can go to a linear combination of x and y such that it will be a new combination. So the two oscillators which had the same frequency, which will have two different frequencies now. So the problem can be exactly solved.
But initially they were degenerate levels.
So the degeneracy will be lifted.
Okay.
because they have different frequencies, n plus half h cross omega 1, n plus half h cross omega 2.
Okay.
The two frequencies are different. So you can easily work out that problem. Take it as an exercise.
Yes.
You will find that with lambda xy, the degeneracy is not there, because as long as lambda is not 0, and that's an interesting point. And when lambda is 0, the degeneracy comes up. That's all is there. Yes? Yes?
Sir, what is the difference between superposition and entanglement, like mathematically?
Okay. Superposition is only mixed state. For example, you can mix various states and you can get a new state. The entanglement issues come up for whether you can express it as a product of a state here and another state here. Only one state here and another state here. You may not be able to. You may have to find a linear combination, a state here, another state here, another state here, a linear combination of them. That's what entanglement will have, whether you can separate them or not. That is where the superposition and mixed thing. Mixed thing is only a simple object. You can mix the states. Okay, you can always mix any vector and get a new vector.
So you mean entanglement is like tensor product and
In
superposition is linear
tensor
combination?
product, it's all coming from tensor product, mixed bipartite kind of this thing, but that whether you can separate them into two parts or not. If you can separate the two states nicely, then there is no problem. But at that separation level, it will require many states here and many states here, and then combined with that. That's what makes a difference.
So separating means with plus sign or some?
Not necessarily plus, it can be minus also.
Okay, yeah, plus minus or?
Yeah, any combination, any linear combination with finally leading to that. Even that state which I had, one spin up, spin down, plus spin down, spin up, or plus or minus, both are entangled states. If I between the two things, that's what will happen.
Thank you, sir.
Okay.
Sir, in the previous lectures we discussed about how when you act a operator and a function, it might go outside the Hilbert space. So, so the Hilbert space.
No,
only
it doesn't go outside the Hilbert space. It goes outside the domain of the operator.
Okay.
It can go outside the Hilbert space also. That is also there.
Does Hilbert space only contain square integrable functions?
Hilbert space by definition is square integrable functions
Okay.
on maybe real 9 or any 2 dimensions, 3 dimensions, any number of them. It should be psi star psi dx should be a finite number. That's all. It should be in this small region. Okay. If something goes to non-zero values at infinity, the particle will be found at infinity. You are not going there. So you should not, that will lead to incorrect. But some cases like plane waves, e power ik dot x minus omega, ks minus omega t, is not square integrable. So that's why we put the whole thing in a box. We call it box normalized. Okay? Or sometimes we adopt that it should be multiplied by the Gaussian function, etc. But that you can make combination of that. Even though e power ikx minus omega t is not square integrable, you can make linear combinations f of k e power ikx minus integral, whereas that f of k is only nice function, small function. Then it will be a wave packet. It's like a wave packet says that this packet is representing the particle. It can be anywhere in that region, but finite region. That's what is it. Okay? This is part of the Fourier transform. If you do Fourier series and Fourier transform, this is a Fourier transform. Yes? Yes. Here.
Sir, I have a basic doubt. Like, we are doing the ladder operations and other measurements, like acting an operator on a function, and we are measuring things. But how does that translate into the physical system? How are we measuring it physically?
Okay, if you want to compare with physical quantities which you are measuring in a lab or this thing, what you have to find out is expectation values and transition probabilities. Expectation value is some state and find the operator some state, that NHI, psi star HI, this thing will tell you, if you measure, it will have a value between these two and the maximum will be here. And that's what you will do experimentally, because that is a number. Any galvanometer will give you a number. So expectation values and transition probabilities. What is the probability if I go in this direction and go in this direction? If I send 100 particles here, how many will be here, how many will be there, how many will be there, what is going to be given by transition probabilities. With one particle, we will say it is a probability. If I say something is here, I send one particle, I ask the question, in this direction, how many, what is the probability? What is the probability to go in this direction? How many will go in this direction? What is the probability, you can ask. If I send million particles, if I say million particles, the probabilities will translate to more or less exact numbers. Okay? For example, if I toss a coin, probability to get head is half, but when you, that's like measuring, but you will get something, either head or tail. So half will be there. If I toss some million times, okay, million times, if I toss, you will get approximately very large number of them will be 500 lakh times will be head, another 500,000 times will be tail. But it will fluctuate in that neighborhood. It will be, it may not be exact, if I do 100 times, 50 and 50, it may be 48 and 52 or 47 and 6. So there will be a distribution. That distribution will be a Gaussian curve. That's what I am saying. So if you want to have exact numbers from this thing, it's a probability, transition probability, and the expectation value will tell you that. Is that okay? That's what the exact numbers when you do the laboratory experiments. That's where we should think in terms of an ensemble of particles, where you repeat the experiments with the same conditions, and you can ask the probability will become, wherein the number is very large. But if there is only one particle, you have to go live with what is the probability. That's all. Okay? Is there anything else? Okay. Thank you very much. Hello.
If I have like, let us say a superposition of like up and down, and ensemble with like up, down.
So if you have a superposition of alpha times up, some beta times down.
Let's say it's just up plus down by root 2. And then
Okay,
like,
so when you do an ensemble, the probability for finding up is half, probability to find down is half. So if you, in the experiments, when there is no magnetic field, a bunch of electrons are coming, the bunch of electrons will have half the number of them will be up and half the number will be down. Now when you apply a magnetic field, up electrons will go up and down electrons will go down. So if you measure in terms of that, it will become up with 1, there is no down, and this is the thing. So the more and more up particles will go there and down particles will. It is there even in your polarization experiments.
No, I'm asking like, let us say I had only like something that measures so some apparatus which only measures like my spin along the z-axis. And then one is like, so I have like two sets of 100 states each. One is like 100 pure states along x-axis, and then the other one is like up by root 2 plus minus.
That's
down,
also
down
pure
by
state.
root 2. No, I mean like up. The density matrix is like up by root 2 plus down by root 2.
Okay.
So like how would I go about differentiating, let us say, the ensemble from the superposition?
So you are going to density matrix, which I didn't talk about. Okay, that's a little more, that's where the issues will come a little more. But for the moment, if I take from density matrix, I can represent that density matrix is an operator. From there, I can immediately relate it to what is the probability it will be up, what is the probability down. That can be computed, and you directly compute that.
In both the cases, I'll get half of them to be up, half of them to be down after measurement.
So that is what the wave function, see, wave function is not a good thing. It's not a measurable one. You can't measure it. If you really want to talk about measurement, I should talk about it only in density matrices. And that's what I directly measure. And that's what density matrices will give. Okay, sorry, my. Yeah, I thought. So finally we. Yeah.
So shall we start? So this is the 5th and final lecture of this mini series on special relativity and classical electrodynamics. So last class we put the whole set of Maxwell's equations in 4 vector form, right? So what did we have? So So first we defined various 4 vectors. I think there was a C over here. I think again there was a C. So please don't believe my C's. Check it for yourself. So given these equations, we had what was the first of set of inhomogeneous equations. We had d alpha f alpha beta is equal to 4 pi by c j beta. Then we had d alpha f tilde alpha beta equal to 0. So we had f tilde alpha beta is equal to half epsilon alpha beta gamma delta f delta. And we had the original 4 vectors transformation. Okay, let's first write x alpha c t x, which is the same as P alpha is equal to E P d alpha is equal to d naught, and we had g alpha beta is equal to diagonal of 1 minus 1 minus 1 minus 1. Right, so we got all this, plus we got the mechanical rate of change of momentum Lorentz force law. We wrote in terms of dp alpha by d tau. So what was tau? Tau was the proper time, right? So it's in the frame in which that object is at rest, right? In that frame you have the least time interval, which is called the proper time tau, and this comes out to be q times, I didn't define it, so let me, okay, I'll just write it first, alpha beta u beta, where u alpha is equal to gamma times c gamma. So in yesterday's class we actually worked through all these exercises, right? We showed that the first set of equations gives you the inhomogeneous Maxwell's equations. I didn't work out the second, I left it for homework. I hope at least one interested student has actually worked it out or will work it out. And we worked out this as well, right? And this I had also talked about in the earlier class, that unlike x components which transforms as a 4 vector, the components of the 4 velocity, which is c comma u, does not transform as a 4 vector, but gamma u being with respect to its particle velocity instantaneously is given by 1 minus u squared by c squared. So gamma times u transforms as a 4 vector, and u itself doesn't transform as the components of a 4 vector. So today what we are going to do is that, having written all this, we are actually going to take one example using the transformation laws, which I haven't yet written down, but using the transformation laws, let us actually see what happens when we have a charge at rest in one field, in one frame, and the charge moving relativistically in another frame. Okay? So how do we understand the transformations, and how do we understand the physical fields? So let us first write the transformation laws. So these are the Lorentz transformation equations. So we wrote x prime alpha, which will be dx prime alpha by dx, which is x beta, which we called a alpha beta times x beta. And matrix form, we wrote x prime is equal to ax, where A is a 4 by 4 square matrix. So that, quickly coming to what we need, f alpha beta prime can be written as two successive transformations, right? So dx prime alpha by dx gamma, dx prime beta by dx delta, f gamma delta, which can be written as a alpha gamma, a beta delta, f gamma delta, or in matrix form, because alpha, gamma, gamma, delta, delta, A transpose. Is this clear? This is what we saw in the last class. So matrix multiplication is just A, F, A transpose. And we will always take, for this little mini series, the simple Lorentz transformation. What did we have? We had x prime is equal to gamma times x minus, Vt, t prime is equal to gamma times t minus Vx by c squared. So y prime is equal to y, z prime is equal to z, right? So what does this refer to? In the frame sigma prime, this object is at rest and it is boosted with velocity v with respect to the frame sigma, which is the frame in which the observer is at rest, right? And this is the Lorentz transformation equations. So what is A now for us? Who will tell me the components of A? Just like we wrote the components of f alpha beta yesterday, now you start by telling me what is the first component of A. See, I have to have x prime 0, right? So this will be A00 x0, right? The first component. So this will be gamma. Now, since we are writing x naught over here, this will become V by C times x naught, right? Because Ct is x naught. So this will be x naught, and then so 1c will go away, and this will become x naught, x prime naught. I hope you can see it, right? I have just rewritten, instead of t prime, I have written Ct prime, because our components now are x naught, x1, x2, x3, right? So, or be like me and set c equal to 1 and don't stress over it, but I think this is correct, okay? So this is gamma, so this is A00. So what is A01? It will be, for the x component, what is it? The t component in the x transformation, right? That is 0, 1, right? Here, x prime 0. So let me maybe write one equation. Where do I write one equation? Here, let me write it here. So x prime 0 is equal to, this I have called A alpha beta, right? So A 0 beta x beta, right? That will be A 0 0 x 0 plus A 0 1 x1 plus A 0 2 x2 plus A, can you still see the board? Yeah, x3, right? So you have written A 0 0 by looking at this equation and looking at the x naught component. A 0 0 was gamma, right? So now you have to look at the x1 component, and x is simply x1, right? So what is the component here? Yeah, so V by C is beta, so it will be minus beta gamma. Good. So now what is this? What is the x2 component in x naught prime and x3 component? And can you see that this is a symmetric matrix? And can you wonder about why it's a symmetric matrix? And now what happens with x0, what happens with x2 and x3? So these parts are 0. So x3 remains, x2 remains x2, x3 remains x3. So you have a unit matrix over here, and you have the xt transformed matrix over here. Is this clear? Is this clear? Okay, so now we cannot rub that off. So we will take away this and put the formula for f alpha beta somewhere, and then calculate the transformation. So we have to think of the problem. So I don't need this, I just need the matrix of f alpha beta. We did this yesterday. So it's just always 0 along the diagonal. This was minus Ex, minus Ey, minus Ez. So what will be here? Plus, very nice, plus Ex, plus Ey, plus Ez. If I tell you that this is minus Bx, what will this be? No, it will be plus By. Easiest way to remember is alternating signs. If this is minus Bx, what is this? Plus Bx. If this is plus By, this is. And if this is minus Bz, this is. Excellent. Okay, so we know all the components of f, and we know that f prime is equal to A, F, A transpose. So these are the stuff that I need to have. So what is my problem? Let me put the problem up here. I have, let us say x1, which is x. Let me just write it as x and y. Okay. So the observer is at rest in sigma. So this is my sigma. Always the unprimed variables are sigma, right? And there is a little charge which is sitting in the x prime. So it is moving with velocity v, and now v will become relativistic. That's the whole idea of this exercise. So v will be moving with respect to, q will be moving with respect to the observer. So here is minus infinity in time, and so as it comes from minus infinity, let us assume that it is going along the x-axis. So it will come from here. At this point, what will happen? We will call that t equal to t prime equal to 0 when the axes of these two coordinate systems coincide. So it will come from minus infinity and go away to plus infinity along the line x equal to 0. And for it, we have to see what is x prime. So after a time t, so that means it is moving with time with velocity v. So after a distance of vt, the particle is here, it is at rest over here. So here is the particle. So this is the charge q, and therefore I will say that the observer is some point p. Theta will keep changing, right? As it moves away, theta will change. So that's the instantaneous value of the angle theta at the time t. Is the problem clear? So if the q was at rest here, then of course the observer will see the nice static electric field, with field lines going radially away from the charge, right? Away from or towards, depending on the sign of charge q. But now this guy is going to go past him like this, and you can see that B is the point of closest approach, what you would call the impact parameter, right? So it's further away here, and then it comes to the closest point, and then it goes away again. So what we want to do is find out what will be the field in the other coordinate, that is for the observer. What will the observer see when the field in E prime, because that is the field, that is the frame in which the particle is at rest. There it is a nice spherically symmetric object. What will the guy in, at P, what will he see? So let us write the equations. So I will divide this into two steps. First I will do the general transformation of F alpha beta, then I will apply it to this problem. Okay. So there are 6 components: Ex, Ey, Ez, Bx, By, Bz. So let us start with Ex. So minus Ex prime is equal to F prime 0. Minus Ex prime is F prime 0, 1, right? What is F prime 0, 1? Let's put some indices here. Alpha, beta, alpha, gamma, F gamma delta, A delta, beta, right? So A 0 gamma F gamma delta A transpose delta 1. Is this clear? For alpha I have put 0, for beta I have put 1. Now you see what are the non-zero elements of A? It is this 0, 1 submatrix and only 2, 2 and 3, 3, right? So the moment you see 2, unless it is 2, 2 or 3, 3, they will all be 0. And only the 1, 0 elements will be non-zero. So who can tell me what this will be? Let us first expand the first example. So I will have to sum over gamma from 0, 1, 2, 3, delta from 0, 1, 2, 3. So what will I get? A 0, 0, F 0 delta, A delta 1 plus A 0, 1, F 1 delta, A delta 1. Now what happens to A 0, 2 and A 0, 3? They are all 0, right? So I stop here. Now I have to do the delta expansion, right? So delta will go from 0, 1, 2, 3. So what will I get? A 0, 0 into, so F delta is 0, 0, 0. This will be 0, you remember, plus F 0, 1, A 1, 1, right? Then what happens when delta is equal to 2? 0, delta equal to 3. So there will be very few terms remaining. So you have to just work this through. What happens to F11? What is F11? Yeah, they are antisymmetric. You shouldn't even look at the matrix, right? So please, somebody tell me what is the answer? Because this is higher mathematics, right? Please substitute and tell me what is the answer. If it's a symmetric matrix, what do you know about A transpose with respect to A? So I don't need to write A transpose for you, right? Did anyone get the answer? Sorry? Minus gamma, check your calculation, or you can peek at the board and see where you have gone wrong. No, but what is substitute for beta squared? What is beta squared? What is gamma? What is gamma squared?
1 over 1 minus beta square.
So that will cancel, right?
That's what I said.
So what will be the answer?
Gamma is
No, those two cancel, it's just minus Ex, right? Gamma squared is defined as inverse of 1 minus beta squared, right? Right? Did everybody get this? Some people who are still trying, I'll give them 1 more minute. You should try, you should try, only then you will get used to it. And there's a minus on this side, and there's a minus on this side, so we get Ex prime is equal to Ex. Now since I know the answer, I am only going to compute the non-zero quantities, so there are only 3 of them, so let us actually do it, okay? Fine? Shall I continue? Someone is still trying it? You want another minute? Okay, why don't you do one thing, try the next one. So what is minus Ey prime in terms of f prime? What is Ey prime? F02, right? F01, F02 and F03 are the electric fields, right? So what will you get here? Only thing that will change is beta, right? So you will get delta 2 over there. So please try it. I'll give you a few minutes to try it. Keep trying, I will write it on the board. Same thing, you have to first expand gamma, then expand delta. So whatever I used, the moment I have a 2 index, I know that the only non-zero elements are 2, 2, that's all. And for 3 it will be only 3, 3, it gets even simpler, right? So that will be gamma minus Ey, A22 is 1 plus 1 is minus gamma beta, right? Gamma beta F02 is minus Ey, A22 is 1, that is minus gamma Ey into 1 minus, sorry, what have I done? Sorry, A01, 1, 2, my 01, this was mistake of mine, F12, sorry, yeah. What have I done? A00, 0 delta plus A01, F1 delta, correct? Okay. So F12 should be minus, according to me, 1 minus Bz, yes, and A22 is 1. So Ey minus gamma into Ey minus beta Bz. That means Ey prime is equal to gamma times Ey minus beta Bz. By the way, in general, this is 0, but you will get this if you did it in the general case. Okay? I'll wait another minute, I can see some people are still trying. Okay. So those who have finished that can find out this. Now I am not going to write the answer. Please try it, everybody. Bx prime, so I have written this now. So 3 0, 3 1, 3 2, right, is plus bx. You could have also taken 2 3 as minus bx, it's okay. I mean. So please try this. You can see that with indices 3 and 2, only A22 and A33 will appear, so it will be extremely straightforward, right? So you can write A3 gamma, F gamma delta, A transpose delta 2, right? So that will be A33, F32. So for those who don't want to calculate, but please do say what is this now, right? Right, everyone understood that only 2 2 and 3 3 which are 1 are going to survive, right? So I will write there is a pattern, it's not that I have mugged it up. And you can see the pattern because I have written them next to each other, right? Is it okay? Okay. And for those of you who are really interested, so this is 1, and F32 is just Bx, right? So Bx prime is equal to Bx. Those who are really interested can try this for an arbitrary Lorentz boost. You can see there is a nice symmetry between these equations, and that is why you have an electromagnetic field which are transverse E and B fields, right? Okay. So those who are interested in checking this out, you can copy it down or look up any textbook, okay? Fine. So now I will have done the transformation of the F alpha beta, and now I will have to apply it to this particular problem. I want those equations, so I am going to clean up this side. So where is the observer sitting? So now we go back to this problem. Observer is sitting at rest in sigma, right? So what are his coordinates in sigma? P has coordinates 0, comma very nice, B, and we have not put because we just want to simplify the problem, right? So he is sitting at B along this y-axis, and he is sitting at rest in this x frame, and of course we just take x3 to be 0, it does not matter to us, right? Fine. So x1 is equal to 0, or x equal to 0, y is equal to b, z equal to 0 is where this observer is sitting. What will it look like in the frame of sigma prime, x prime? X prime is equal to gamma times x minus Vt, but x equal to 0 is minus gamma Vt, and T prime is equal to gamma times T minus Vx by c squared, which is just gamma T. So this is equal to minus V T prime, right? Because this is gamma T is T prime. And that you could have just said, right? Since he is sitting at rest and the charge is moving away with velocity v, it looks like it is receding with minus Vt prime, right, from him. So this is the transformation laws. So now that we know these x and x prime, what let us write now with these things? Let's start with E prime. So what are the coordinates of E prime? What is E? First of all, let's write the vector E. The vector E prime. E prime is where the charge is at rest, right? So when the charge is at rest, you have this radially outgoing field. So what is the electric field due to a point charge q? Okay, my 1 by 4 pi epsilon naught is equal to 1, so I don't worry about it. So what do I have? Q by very nice, q by r prime squared. We are in E prime, right? And the direction is of course some unit vector. What is that unit vector? It has components, so if I write it as r cube times r, so I can write it as q by r prime cubed into vector r prime. It will have coordinates of this and then b and then 0. So let me write each of these components. Ex prime is equal to q by, what is r prime now? R prime is, where will I write it? Here maybe, because y prime is equal to y, z prime equal to z. So r prime is equal to root of x prime squared plus y prime squared plus z prime squared. That is equal to x minus vt squared plus y squared plus z squared. Right? So this will be this object to the power of 3 by 2 because there is a square root. Okay. And what is the x component? Minus vt prime. Right? Sorry, this is not for full E. I have written it in the wrong place. It is for this guy. So q by, so for y let me put b, for z let me put 0. So I will have b squared plus let's call it x prime squared to the power of 3 by 2 minus gamma minus Vt prime. Now I can write that as, what is T prime? Gamma T, right? And what is x prime? It is gamma Vt. So I can write this as b squared plus, so what have I done? I'll just tell you what I have done. I have written everything in terms of x and t. So I have E prime, which is written in terms of t prime and x prime, but then I have simply substituted in terms of x and t using the Lorentz transformation equations. So let me write down all the equations over here on the side. Ex prime is equal to minus qvt prime, so that will be gamma vt by 3 by 2. So this was x prime. Y prime is simply y, which is just b. Ez prime is 0. Bx prime, by prime, you can take it out, will come out to be 0. Bz prime, you can see here there is a non-zero Ey. So we had only non-zero Ex, Ey, right? So that will give me Ex prime, Ey prime, this will be 0, this will be 0, this will be 0, but Bz prime will be minus gamma beta Ey. Minus gamma beta. Is it okay? So you can see immediately that once I have done the transformation, I started out with pure electric field in x and y direction, and now I have generated a magnetic field in the z, which you will immediately observe is transferred to both Ex and E, right? So now let me write where will I write? Okay, we will remember this equation and write here. What I want to do now, I want to write down is the E prime field, right? So E prime is the field in the prime frame. Okay? Obviously, I'm really sorry. This is the frame in which the guy is at rest, charge is at rest. Okay, so there's only Ex and Ey field. But now you can see that if I apply these inverse transformations, it means Ex is Ex prime, Ey is gamma Ey prime plus beta by changing V going to minus V. Then as I said, I will generate Ex is equal to Ex prime, Ey is equal to gamma Ey prime and Vz is 0 and Z is equal to gamma of everything is 0, so Vz will remain 0 and Vx prime will be Vx is equal to Vx prime and as I said Vy will be Vy prime and Vz will have gamma times Vz prime 0 minus beta have it inverted. Okay? So now that I have this, I can write them all down. Let me write them down. So Ex and Ex prime are the same. So Ex is simply that minus Q gamma Vt by, okay. So Ey will become gamma times, where am I? Ey is gamma times Ey prime. Ey prime was minus QB by, and Ez prime all are 0, only Bz is there, will become minus gamma beta Ey prime was plus QVB by this to the power of 3 by 2. Okay, so now we have done the transformations, right? Now let us try to interpret them. So to interpret them, let me write the diagram again. So now I am only writing sigma x, y, this is P, and as I said the charge comes from here, and at some time t it was here at an angle theta. So this r is the instantaneous direction from where that charge is sitting to the observer. So the observer is at rest, and as the charge is moving away from the observer, Rp will keep increasing, right? So this is because in this frame, in the x prime frame, that is in the sigma prime frame, the charge is at rest and there is a uniform E distribution. But now because of this Rp, you can see that Rp has coordinates just from geometry. But this denominator, I rubbed it off, has the same coordinates with gamma Vt over here, right? You remember, because it was expanding by gamma times Vt. So I know I have to find a relationship between these two, and the way to write the relationship is as follows. Okay, I have something to say before I do that. Okay. Okay. So before I do that, you notice that Ex prime is a function of t in the numerator, Ey prime and Bz prime have no t in the numerator, right? So that means when t is going from minus infinity to infinity, Ex will actually change sign as you cross the origin, whereas Ey and Bz will not change sign. Is it clear? So that means if I want to plot this, so what is the denominator of this here? It was b squared plus gamma squared v squared t squared. We are still in the, right? So when t is equal to 0, Ex is 0. When t is negative, Ex is positive. When t is positive, Ex is negative. And because of this gamma, and we know that this is a relativistically moving particle, this is going to damp very quickly, because this is some a plus bx squared, because as the t increases, but this is enhanced by gamma squared. So very quickly these are going to fall away. So how will this, maybe I will draw it bigger. So how will it look as a function of, so typically what is plotted is as a function of gamma Vt by B, because you can see that this is, what is the units of gamma Vt by B? Huh? No units, correct, because B was the length in the y direction, Vt is the length in the x direction. So it just tells you like the relative size of this component with respect to this component, that's all. And this is the one that is increasing, right? B becomes very small, so you don't really care about it. So that is why you write in units of B, the denominator is, if this if I call this some k or something like that, you can see that the denominator is actually 1 plus k squared to the power of 3 by 2, right? So as k increases, this is falling as 1 plus k squared. So how will it go? So at minus infinity, the denominator is going to, because it's going to be increased by gamma squared, right? But in fact, long before infinity, it will go away to 0. Then it's an odd function, and then it will come back here, right? This is x and this is Ex, right? You can see that because of this t, the sign changes. However, Ey and Ez, as you move away from t equal to 0, it will simply be a positive guy. So we will just pick a positive guy. And of course, all of them will die away as you go to plus minus infinity, right? So this axis is, sorry, oh my God, what have I said? This axis is this gamma V t by B. So basically, gamma is a constant, V is a constant, B is a constant. So in some arbitrary units, it indicates the passage of time. Okay, and then of course, once I had, this is Ex now. Now I have plotted Ey, and of course Bz will be the same, because we saw that it was just a factor times that. So we just multiply it by some other constant. Okay, and the larger gamma is, I hope you can see that, the narrower will be this pulse, because the denominator is going to go away, become larger and larger when gamma gets larger and larger. And when gamma goes to infinity, you can see that you will just get a delta function, right? Because when t is equal to 0, you will have some number, and then when you just immediately go away from it, you will have nothing, right? So this is the distribution that you have. So what the person will see, therefore, is a combination of all these fields, right? He will not see separately Ex and Ey, of course Ez is 0 and Bz, but what he will see is that this Ex component, it passes by in a flash, flips sign, he is not going to see much of it. What he is going to see is that he is going to see Ey and Bz, which are crossed electric and magnetic fields. So in the limit that gamma is ultra relativistic, he is actually going to see an electromagnetic pulse, because he will see Ey and he will see a transverse Bz. Is it clear? So to show that, we will actually write yeah.
Passes the observer.
Sorry, when the Ex will be exactly 0 when the charge is at 0, right? Because
Exactly
t equal
where
to
the
0,
observer
no?
is.
Huh?
That's exactly where the observer is.
But observe, that's why you see we are very smart and we have displaced the observer by B.
Okay. Yes.
Right?
Yes.
That is done in advance, because you know this is the problem otherwise. So they are not actually, it's not as though the charge is going to actually overlap with your position, your safe distance B away.
Okay.
So that's what you are watching, right? That is the thing. So that is why the P is not here. The P is not here, P is shifted away. So the charge comes from here and exits on the side. So it's just whizzing past you with relativistic speed. So if it is going very slowly to the limit that V goes to 0, then you will only see a uniform or almost uniform electric field due to a quasi-static charge. But the moment he picks up speed and he starts going past you, that charge is going to look like a crossed electric and magnetic field. Okay? And you see that we don't have to worry too much about the derivation, we don't have to worry about how to look at the components in the electric and magnetic components, because you're starting with a very simple electric field and using the Lorentz transformation equations to just give you the solutions in the moving frame, right? So where was I? Sorry, I was doing this calculation. So now I need this board, so I will rub this off. No, I needed this, yeah, it's okay. So let's, okay. Okay. So there's one more observation. Okay, I think I have it here. Let me write it again. Bz is equal to gamma beta times Ey, right? QB by, which is essentially R cubed, right? Let's write it as R cubed. And you can show that this is the same as Q by C V cross R by R cubed. What does this look like? What does this look like? While I'm doing this, somebody can tell me. Okay. So this is exactly the Biot-Savart law for a moving charge, right? Right. So you could have started, you don't know anything about Lorentz transformations. You're just in the frame when the charge is moving. What is a moving charge? Moving charge is like a current dq by dt, right? Or you can write it as rho v or whatever, and then you can write the answer and you will get this, right? So this is essentially exactly that. QV is what will give you your current, and that is the Biot-Savart law. So you could have just started with this, don't know anything about Lorentz transformations, and get this. So this is the second point I wanted to make. Okay. Now I want to write this in the coordinates Rp, so that we can make some more deductions about this charge. So the way we will write this is, okay, this I am going to leave as exercise for you. It's just very straightforward. So x prime is gamma x minus gamma beta t plus y squared is b squared, we call it if you want. It doesn't change, okay. Now you can expand this, okay, and write, because you know that tan theta or sin theta, you can write sin theta is equal to b by rp. So you can replace this coordinates by the rp coordinates and you will get rp squared into gamma squared cos squared theta, very straightforward actually, plus sin squared theta, which I can again rewrite as rp squared into 1 minus beta squared sin squared theta. I don't want to waste time doing this, that's why I am just writing it down. So my denominator, which is that to the power of 3 by 2, will just become rp cubed and this to the power of 3 by 2, right. So now let me write the fields again in terms of this. So E, so okay, I will leave that also, like write Ex, write Ey, write Ez, and then write the vector E, okay, so that I don't waste time. This should not surprise you, right, because that is the instantaneous direction and it is radial field divided by r p cubed into, so I hope this gamma and r doesn't bother people, gamma squared into 1 minus beta squared sin squared theta to the power of 3/2 into, so sorry, let me solve it to give you 1 minus beta squared in the numerator, okay. Okay, this is just requires some steps. You have to substitute this in these expressions and bring it back and look at E. I am not looking at B, I am only looking at E, okay. Fine, I have just substituted and it's just 3 lines to do that. So 1 minus, the velocity is a constant, so 1 minus beta squared is some constant, okay, doesn't matter, and Q is a constant. So the denominator is what is changing, right. So for a given rp cubed or a given distance rp, you can see that this sin squared theta will decide what the denominator looks like. So the larger that, so when sin theta is 0, this denominator is 1, and when sin theta becomes larger and larger, this denominator becomes smaller, so that E becomes larger, which means E is largest when theta is equal to pi by 2, when sin squared theta is equal to 1, right. So if you now look at how these field lines are going to look, so in the sigma prime frame, the charge is at rest and the field lines are radiating in all directions. So let's write radiating in all directions like this. Okay, they are uniform. This is supposed to be a circle, but it didn't come out quite that way. But now what happens? The field lines become larger and more dense because the field is larger. That's what the field lines represent, right, in the transverse direction. So the total flux will remain the same because this is just the pulse. If it is slow, it is integrated over a larger distance. If it is fast, it is integrated over a smaller distance. So the same number of field lines, I have carefully counted it. So if you look at this transverse direction, so this is always the motion of the particle in the x direction. So you will find that it gets squeezed more towards this value. So you have one like this. So this is called the broomstick, okay. So ultimately if you have extremely relativistic charge, then you will simply have a field which is completely transverse and with very little field on the sides, okay. So it squeezes the field lines into the transverse direction. That is what this is telling you. And because B is in the transverse direction, you will get again squeezed field lines. The denominator was the same for B as for EY, right? So you will get the same denominator. And so what you will get is a very, very sharp pulse, E in the transverse direction to X, and B even further Z direction also transverse to Y, EY, okay? So this is what you will get, and so the observer will actually see, maybe we should have even more lines over here and very few lines over here, okay? This is what you will get, and so he will see an electromagnetic pulse. So I want to make one last remark which I will not derive. So as far as the observer is concerned, he says that it's an electromagnetic pulse, right? He doesn't know that it is actually a charge, point charge, right? What he sees is an electromagnetic pulse. So because you know that it's an electromagnetic pulse, you can actually calculate the Poynting vector, which codes for both the energy and momentum. You remember S by C squared was the momentum. So you can actually calculate this, which I am not going to do. I am just going to write down the answer and interpret it. Same denominator, that will not change except for the power, and it will be in the direction of theta. If you want, I can actually fill this in, having written so much. Okay. So this is the Poynting vector. Now I can ask, what is the flux due to this? This is the energy generated. So what is the flux in some finite volume? So in some finite volume over the surface of that finite volume. So I have a volume V and its surface A. So what is dA? dA is r squared d cos theta d phi, right? That is we talked about it in the first class, and this is, so I am not going to do the integration, I am just going to point out that, so this goes to 0 very quickly. What is the significance of this? The question is that now I have a moving particle and I have generated all kinds of electromagnetic fields. Is this going to radiate? This doesn't radiate because if I have radiation, the radiation pattern must extend out to infinity. It cannot die as 1 by r squared. Okay? So that means it is still not an accelerating particle in any frame. It remains a constant velocity particle in all frames, and therefore it does not radiate. So this is a very important question. So you can, as long as you are going from one inertial frame to another, you are not going to have any acceleration, and therefore there is no radiation. It is just that this static electric field is seen as an electromagnetic pulse. Is this clear? So this is one example of how you can apply the transformation laws to very quickly get the answer. I can't draw, but you can, there are a lot of visual aids online. You can see that the magnetic field will be azimuthal, so you can go and look it up. I certainly can't draw azimuthal magnetic fields, so you can go and find out. So in the last 15 minutes, I want to spend, okay, so I forgot to say this thing. So basically it looks like you are compressing all the fields in the transverse direction, and that is again another effect of Lorentz contraction. Okay. So I am going to just highlight here. I am not going to really do much. I just want to end this because now we have got so much stuff. What do we usually do when we put all this together? We write a Lagrangian. Okay. So I am going to outline the Lagrangian formulation of electrodynamics. I am certainly not going to complete this Lagrangian formulation of electrodynamics. So there are two different sectors. I will not talk about the fields at all. Okay, that is a, a much bigger problem, and I don't have the time to do that. So what I will talk about is what we have talked about here. We are talking about how the electromagnetic field influences the motion of particles. So we are going to look at the Lagrangian of particles in electromagnetic fields. That means the Lagrangian, we write Lagrangian is T minus V, right? Kinetic energy minus potential energy. Kinetic energy will be for the particles, and the potential will be the potential that the particle sees in the electromagnetic field. So they will also be the kinetic energy of the fields themselves, but that is left for the future, okay? So I am not going to do that. So what do we want then? You want to get the equation. This equation now we have seen 100 times. What have I done? Earlier I had put the m on this side and I had called it dp by d tau, right? dp alpha by d tau. If you want, I can still call it dp alpha by d tau, but Lagrangian is a function of q's and q dots and not of p. So I have taken the p and called it m times capital U. You remember capital U was? What was capital U? Very nice, gamma times c and u, right? So I want a Lagrangian which actually whose Euler-Lagrange equation of motion is this. First thing you have to notice is that what is the property of the action under Lorentz transformation? It's an invariant, right? It's a number, it's invariant. If A is invariant, it means LDT is invariant. But dt is not an invariant, it's the time component of a 4 vector, right? So what I can immediately see is that if I write this as gamma L d tau, what is the property of d tau? It's an invariant. So what should gamma L be? Okay, so then I have to write gamma L. So gamma L should be the invariant, and in fact immediately I will tell you that for a free particle in the absence of any fields, so gamma L is an invariant, obviously mc squared is an invariant, and what you have to do is, what are the Euler-Lagrange equations of motion? Every one component, but you can increase it to whatever number of components you want, right? If you want to write it as q and q dot, we can write it as q and q dot. If this looks more familiar to you, then we can identify q and q dot as the x and u dots, right? Sorry, x and u's. So please do this as homework, and what will you get immediately? So you will get d by dt of mu gamma is equal to 0. What was mu gamma? The momentum, 3 momentum, right? And therefore, here from m times u gamma, right? And it tells you that if in the absence of an external force, momentum is conserved, right? So that's all. So that is the answer, and that is straightforward. Now what you have to do is take this free particle, that is the kinetic energy term. The minus was required because the gamma in the denominator will give you a minus sign when you differentiate with respect to u, right? So that is why that minus was there. Now you have to add a minus potential energy term. Okay? What is this? Suppose I just have pure electric field. What is the potential energy of a charged particle in the electric field? Q phi. So I just have to add a minus Q phi. So now I have to guess over here. I don't have only Q phi, I also have A. And we already saw this in the last class. So I have L, did I put gamma here or there? 1 second. Okay, so let's write first the interaction term. Will be minus E. So I have still the gamma here. E by gamma C, U alpha. And if you expand this, you will get this part to be minus, okay, the whole part will be minus E phi plus E by C U dot A. And if you use this Lagrangian, what should you get then as the Euler-Lagrange equation of motion? You should get back Lorentz force equation, right? So I will leave you to do this. Will you work this through and make sure that you get, it's not very difficult. The only thing is that because of the motion, you will have to write d by dt is d by dt plus u dot del, and then you will get all your answers. So please check that. This will simply give you the Euler-Lagrange equation, that d by dt of p, which is gamma mu, will give you E by C, I don't remember the C part, please forgive me, E plus V cross B. This is your, so this is your force law, right? Rate of change of momentum is the force, and F is equal to QE plus V cross B. So you can work this out. You have seen this before and you can work it out. However, you can see that I am still working with components. I am working with components U and del and E and B and things like that. I want to be able to write a manifestly covariant Lagrangian, right? So for that, there is a trick that is used. You remember that L was minus mc squared by gamma, which I can write as minus mc squared root of 1 minus u squared by c squared. And I can write this as minus mc into c by gamma. It is simply because u alpha is c squared. And the reason we do it is because nowhere in this have we used this constraint. We have implicitly used it, but we have not explicitly used it. So what we are going to do is that we are going to write a Lagrangian like this in terms, I hope you realize these are the capital U's. I hope they are big enough, right? U alpha is c squared. Gamma squared into 1 minus beta squared we just saw was 1, right? So it is just c squared, right? So we just want to make sure that we have a form of this type, and then in the end we will set u alpha is equal to c squared, and so we will be able to put in the constraint like this through this form. So we can write this as minus mc by gamma integral u alpha u beta g alpha, which I can write as minus mc So A is equal to gamma L minus mc root of u alpha d tau u alpha d tau. Yeah? Yes, sir. Huh? No, I know. That's why I'm stopping over there. I'm not writing beyond that point. What is not visible? Oh, they've zoomed it, is it?
Yeah, because the camera is.
Okay. Sir? Who is there? Gayatri is there? No? Okay, doesn't matter. Let's not disturb them. Let me write it somewhere else. Thanks for pointing it out. Now it's, no, even now it's not there. Okay. Okay, fine. People are clearly reading the board. So let's just write A is equal to gamma L, and I wrote gamma L as 1 by gamma gets cancelled minus MC. So d tau, sorry, minus MC d tau of u alpha that I can write as minus MC from some tau 1 to tau 2, which the endpoints are invariant, blah blah. So dx alpha by d tau, dx beta by d tau, g alpha beta d tau that's equal to minus mc dx alpha dx beta g alpha beta, that is equal to, I am using a trick here which is very standard, dx alpha. I will explain to you. So what I have done is that I have got rid of my tau, and you remember the world line of the particle, I have now parameterized it by some monotonically increasing s. And what I say now is that instead of tau I just have s which keeps on increasing, and then I can write everything in terms of this s, and therefore s goes from s1 to s2, the endpoints are held invariant, and then you can again derive the Euler-Lagrange equations of motion. Okay. So now once I do it this way, what will I get as my Euler-Lagrange equation of motion? D by ds, because that now codes for tau or t of d. Now this L is now written in terms, so I call it L tilde because now this is my, so this part minus mc square root is now my new L by d of dx alpha by ds, which is now dx, that is the advantage, dx alpha by ds is equal to dl by dx alpha, right? Same thing. Now you can do this, it's extremely straightforward to do this. I can't write there, I will write here. And when you do this, you will get the Euler-Lagrange equation m d squared x alpha, and then I am going to substitute back for tau. I just want to interpret this, I am not going to do more with this. You can work this through. d beta d alpha into dx beta by d tau, which is q f alpha beta times dx. So now we have tau is an invariant. Okay, so this is beta and beta is summed over. This is x alpha. This is some. This whole thing is some vector of alpha, and so now I have completely covariant equation of motion. Okay, so this is the equation. So this is the Lagrangian that I can choose, and when I choose this Lagrangian, I will get the right equations of motion, and I have done some little bit of massaging in order to write it in the manifestly invariant way or covariant way. However, how will I get a Hamiltonian out of this? So if I have a Lagrangian of q dot, how do I get the Hamiltonian? I will define the conjugate momentum and define this as the Hamiltonian, right? However, there is a problem at this point. Can anyone tell what will be the problem if I define a Hamiltonian like this? What is the Hamiltonian code for? Energy of the system. So what should I get? What should be the property of this Hamiltonian? It should transform like the time component of a 4 vector, right? And this is simply a scalar quantity, it will not do that. So we get stuck here, and then we will have to find, that's why I didn't want to spend too much time on this. You will find alternate paths to writing proper Lagrangians and proper Hamiltonians, but this is to show you that there is a glitch here, and therefore you cannot proceed in this direction. You will have to find a different way of doing the whole thing. Is it clear? So this Hamiltonian will just be a scalar, but you cannot have a scalar Hamiltonian. It has to have energy or time-like properties. And so even though you have managed to write a manifestly invariant Lagrangian, which gives you covariant equations and the correct covariant equations of motion, you cannot continue this into the Hamiltonian formulation. Okay? So basically what we did was, I took the knowledge that you already had of Maxwell's equations and I recast it in a form which is very convenient for later times. And if you want to go from special relativity to general relativity, this kind of, writing in terms of alpha, beta indices and compacting the equations into very small stuff and will help you to actually do the calculations much easier. There is no more content in the covariant formulation of Maxwell's equations than in the explicit construction of the Maxwell's equation. They code for exactly the same thing. It is just that if I say d alpha f alpha beta equal to j beta, and then it's like wonderful, it sounds very good and compact and nice, but as I said, the original equations code for the same information. Okay. However, if you want to go towards more exotic space times or curved space times, then this kind of notation can become very useful. Okay. And when you are wanting to go towards a complete Lagrangian for the combined system of the fields, the particles and the interactions between them, then this notation is kind of, without this it will be very hard for you to actually be able to put together a Lagrangian which will have the correct properties and which will transform also correctly. So this is the advantage. You have now manifestly invariant or covariant sets of equations. Okay. So those who are curious, you can actually go, if you find the Lagrangian anywhere, and it will be everywhere in any textbook, you can actually see for yourself by applying Euler-Lagrange equations of motion that Lagrangian will give you the correct equations of motion. We know that the Lagrangian is never unique. I can always add terms to it such that the equations of motion are not changed. The equations of motion are the physics which we have already discovered. So the way in which we implement it is just like the Lagrangian is there for convenience. Again, it is the between equation of motion and Lagrangian, neither is superior. Okay. Again, it codes for the same thing, right? But sometimes the Lagrangian gives you insight because it tells you this is the kinetic energy, this is the potential energy. It tells you the structure of the interaction. The potential energy gives you the interaction that A alpha, U alpha tells you the nature of the interaction between this, where is that, I rubbed it off, but you remember that we had written the interaction as A alpha Q by C, A alpha U alpha, right? Now U alpha is little vector U and Q times U is like a current J. So actually this will end up as the interaction current A alpha J alpha. Okay, and this J alpha, this J dot A interaction, you will find everywhere when you do your quantum field theory. So the source or the origin of that J dot A interaction has its beginnings from classical electrodynamics. Okay, is it clear? Okay then. So it was nice. I don't know, I hope you got something out of the lectures. I enjoyed giving them. So I'm done with this course. Thank you very much. If there are any questions, you can ask. Yeah. Okay, because I didn't show you those steps. Somewhere at some point I have to impose the condition that U alpha is C squared. Okay, and then this becomes a convenient way to do it. So since I didn't show you all the detailed steps, I cannot actually, unless I work through those steps. But this kind of representation you will find will become very common when you go to GR. Okay, so I just wanted you to see this. So if you see a Lagrangian which has square root of G alpha beta, then you know that it is nothing more than just fixing the invariant quantity, right? That's all. Okay, fine. Okay, let us go for lunch. Oh, sorry.